Close your eyes for just a moment. Imagine you are floating, not above a city, not above the clouds, not even above the earth itself. You are floating somewhere much farther away, somewhere so far that the sun behind you has shrunk to the size of a bright coin. The darkness around you is absolute, a deep, perfect silence that stretches in every direction for hundreds of millions of miles. And then, slowly, you turn. And there it is, hanging in the void like something that was never meant to exist, a world so beautiful, so geometrically impossible, so overwhelmingly large, that the human mind struggles to process it as something real. Saturn, there is no planet in our solar system quite like it, not even close. Scientists who have spent their entire careers studying it still pause when they look at new images. Astronomers who have seen it through telescopes for decades still feel something shift inside them when they catch it in the night sky. Because Saturn doesn't look like a planet. Saturn looks like a painting, like a dream someone had about what space should feel like. Those rings, those impossible, magnificent, confounding rings, they stretch nearly 175,000 miles from one edge to the other, wide enough to place dozens of Earths side by side across their diameter, and yet they are, in most places, no thicker than a 10-story building. Thinner, proportionally, than a sheet of paper held up to a dinner plate. Something about that fact is deeply unsettling when you really let it sink in. All of that scale, all of that grandeur, balanced on an edge so razor-thin that the universe seems to be defying its own rules. But the rings are only the beginning. Because Saturn itself, the planet beneath those rings, is hiding things. Extraordinary things. Secrets that scientists are still piecing together. Mysteries that grow stranger the deeper we look. And questions so fundamental that they have changed the way we think about how planets form, how weather works, how moons are born, and what our solar system might have looked like billions of years ago. In the centuries since Galileo first looked up and saw something strange on either side of Saturn, something he described as two companion bodies, because his telescope wasn't powerful enough to resolve the rings, we have been obsessed. We have sent spacecraft. We have built instruments beyond anything Galileo could have imagined. We have calculated, observed, debated, and discovered. And yet, the more we learn about Saturn, the more it reveals how much we don't understand. Why do Saturn's polar regions hold geometric storms that seem to violate the basic physics of atmospheric behavior? Why does the planet emit far more heat than it receives from the sun? And where exactly is all of that energy coming from? Why do its rings contain water ice that is startlingly pure, when every known source of water in the outer solar system is contaminated? How did a moon the size of Texas manage to hide a liquid ocean beneath miles of frozen shell, and is something alive in that ocean right now, at this very moment, in the darkness, under the ice? These are not theoretical questions. These are things scientists are actively working on. Real researchers, real observatories, real data collected by real spacecraft that we built and sent across the solar system specifically to find the answers. And what they have found is extraordinary. What they have found is that Saturn is not just a planet. It is a system, an ecosystem, a world of worlds, presided over by a giant of swirling gold and cream and amber, surrounded by a family of moons so strange and diverse they seem to belong to different solar systems entirely. Some of those moons may be the best candidates in our entire solar system for finding life beyond Earth. Let that settle for a moment. Not Mars, not Venus, not some distant exoplanet thousands of light years away. Right here in our own cosmic neighborhood, orbiting a planet we can see with the naked eye on a clear night, there may be environments where life is not just possible, but actively sustained. We are going to journey through all of it, together, slowly, without rushing, without skipping past the wonder, without reducing any of it to a list of facts. This is a journey through the greatest secrets of the most beautiful planet in our solar system. This is Saturn. And we are only just beginning. Before we go further, I want to make you a promise about this journey. We are not here to recite a textbook. We are not going to rush through Saturn like a checklist. Rings, moons, storms, done. What we are going to do is something much more interesting and much more rewarding. We are going to peel back Saturn, one layer at a time. And every single layer we remove is going to reveal something that raises a new question. A deeper question. A question that makes the one before it seem almost simple by comparison. That is the nature of Saturn. That is why astronomers love it so deeply. Not because it gives clean answers, but because every answer it offers opens a door into a room you didn't know existed. Here is some of what waits for you in the hours ahead. We will look at the rings, not just what they are, but what they might tell us about the history of the entire solar system, and why some scientists now believe the rings are far younger than Saturn itself. We will ask, if the rings are new, what happened to destroy whatever made them? And the answer to that question is genuinely strange. We will travel to the North Pole of Saturn, where a six-sided storm the size of 2 Earths has been spinning without pause for as long as we have been watching. We will try to understand why it is a perfect hexagon, not an oval, not an irregular shape, but a geometric figure so mathematically precise that it looks engineered, and why no other planet in the solar system has anything remotely like it. We will visit Titan, Saturn's largest moon, a world wrapped in an orange haze so thick that spacecraft sent to study it couldn't see the surface until they were almost upon it. A world with lakes, rivers, seas, and rain, all of it made not of water, but of liquid methane. A world where the chemistry of life might be operating on completely different rules than anything we know. And then we will go to Enceladus, a small, icy moon, gleaming white against the darkness, quiet and still and almost overlooked for decades, until scientists noticed that it was erupting. Giant plumes of water vapor and ice crystals shooting hundreds of miles into space from cracks at the moon's south pole. Plumes that contain organic molecules, molecular hydrogen, silica particles that could only form in hot water near a rocky seafloor. Everything, every single chemical ingredient, that life as we know it needs to begin. We will explore Saturn's impossible interior, where the pressure is so extreme that hydrogen stops being a gas and becomes a metal, a fluid metal that conducts electricity, spins with the planet, and generates a magnetic field that is both massive and deeply strange. We will ask why Saturn's magnetic field is almost perfectly aligned with its rotation axis, which is something our models say simply shouldn't happen, and what that misalignment, or lack of it, might be hiding. We will look at the storms that rage through Saturn's atmosphere, not just the hexagon at the North Pole, but the great white spots that erupt every 30 years like clockwork, global catastrophes that scientists are still trying to explain. We will ask what is beneath those clouds, what deeper layers exist below what we can see, and whether the interior of Saturn holds secrets that no spacecraft has ever been close to understanding. We will talk about time, about how long Saturn has existed, about whether the planet is still changing, still evolving, still becoming something different than it is today, about whether billions of years from now Saturn's rings will be gone, and what will replace them. And finally, we will pull back, very far back, until Saturn is small again, a point of light in the darkness, and we will ask the oldest and most human question of all. What does it mean that we, small creatures on a small planet, learn to wonder about all of this? What does it mean that we built machines and sent them across the void purely because something beautiful caught our eye? Saturn has been waiting 4.5 billion years for someone to ask. Let's begin. Let's start with what you see first, what everyone sees first, the rings. If you have ever pointed a telescope at Saturn, even a modest one, even a backyard instrument barely powerful enough to resolve the disk of the planet, you have seen them. And almost everyone who sees them for the first time has the same reaction. Not excitement, not scientific curiosity, something quieter than that, something that feels more like recognition, as if some part of the mind had always known this shape was possible, had been waiting to see it confirmed. But here is where the rings start to get strange. Here is where what appears to be pure visual beauty reveals itself to be one of the most confounding structures in the solar system. The rings of Saturn are not solid, not even close. They are not a flat disk of material, not a continuous surface you could land on. They are composed of hundreds of millions, perhaps hundreds of billions, of individual particles. Ice, mostly, water ice, ground to sizes ranging from tiny grains smaller than a fingernail to boulders as large as a house. All of them orbiting Saturn in perfect gravitational lockstep, maintaining their positions relative to one another with such precision that from a distance the structure looks seamless. But the moment you look closely, the rings dissolve into chaos. Every particle is traveling its own individual orbit, colliding gently with its neighbors, absorbing and reflecting sunlight, being nudged by the gravitational influence of Saturn's moons, being sculpted constantly by forces that act on the smallest scales and produce effects visible from Earth. The rings are divided into distinct bands, labeled alphabetically in the order they were discovered, which means they are not in alphabetical order from the planet outward. A small piece of scientific trivia that has confused students for generations. The main rings, the broad, bright ones visible in even modest telescopes, are the A ring, the B ring, and the C ring. Farther out, harder to see, are the F ring, the G ring, and the E ring. Each one slightly different in composition, each one carrying slightly different mysteries. The B ring is the brightest and most massive. It is so reflective, so packed with ice particles, that it sends sunlight back into space with almost the efficiency of fresh snow. If you could somehow compress all the material in the B ring into a single object, you would have a body roughly half the size of Mimas, one of Saturn's small inner moons. That is the total mass of the most visible structure in the solar system, roughly half a small moon, spread across a disk wide enough to span the distance between Earth and the moon and still have room left over. But that wasn't the strangest part. When the Cassini spacecraft, NASA's extraordinary mission to Saturn that spent 13 years in orbit around the planet and revolutionized our understanding of the entire system. When Cassini measured the rings in extraordinary detail, it found something that should have been impossible. The ice in the rings is too clean. Space is not a clean environment. The outer solar system is full of dust, micrometeorites, carbon compounds, silicate particles, microscopic debris raining constantly through the void. Over billions of years, this material accumulates. It tarnishes surfaces, it darkens ice. Every icy body in the outer solar system, every comet, every Kuiper belt object, the icy moons of the outer planets, they all show signs of this contamination. They are gray, or brown, or reddish-brown, stained by billions of years of accumulated cosmic dirt. Saturn's rings are not. Saturn's rings are white, nearly pure. The ice in them has not had time to accumulate the level of contamination you would expect if it had been sitting in space for 4.5 billion years, the age of Saturn itself. Scientists looked at this data from Cassini and reached a conclusion that fundamentally changed how we think about Saturn. The rings are young, geologically, cosmically young. Between 100 million and 400 million years old, current estimates suggest. Saturn formed over 4 billion years ago, long before the age of the dinosaurs on Earth, long before complex life of any kind had appeared on our planet. But the rings? The rings formed during the age of the dinosaurs. The rings appeared in our solar system roughly around the time Stegosaurus was walking the Earth, which immediately raises a question, a fascinating and slightly unsettling question. If the rings are young, if they weren't there when Saturn first formed, where did they come from? Something made them. Something was destroyed. Some object, a moon, a large comet, some icy body of considerable size came too close to Saturn and was torn apart by tidal forces. The gravity of Saturn is so overwhelming at close range that any object approaching within a certain threshold, astronomers call it the Roche limit, is simply pulled to pieces. The planet's gravity pulls harder on the near side of an object than the far side, and if the difference is great enough, the object's own structural integrity cannot compensate. It fragments, it disintegrates, its pieces spread into a ring. But here is where the mystery deepens. Here is where one answer creates 3 new questions. What was the object that was destroyed? How did it get close enough to Saturn's Roche limit in the first place? And is this a one-time event, the rings as a remnant of a single ancient catastrophe? Or is it an ongoing process, with new material constantly being added and old material constantly being lost? Because the rings are not permanent. They are not a stable structure that will persist indefinitely. They are being eroded, steadily, slowly, but measurably. The sun's radiation charges the ring particles, and Saturn's magnetic field then pulls some of that charged material down into the planet's atmosphere, a process called ring rain. Cassini measured it directly. Saturn's rings are losing material at a rate that suggests they will be entirely gone in perhaps 100 million years. The rings of Saturn, the most iconic feature of our solar system, the shape that appears on textbooks and posters and the logos of space agencies around the world, are temporary. We are living in the exact geological moment when they exist. Give or take 100 million years in either direction, and there are no rings. Yet another mystery emerged from this discovery. If the rings are young, and if they are disappearing, if they represent a brief moment in Saturn's long history, then how many other ring systems has Saturn had? Did earlier moons get destroyed and create earlier rings that have since vanished? Are there ghosts of former rings embedded in the cloud tops of Saturn? Remnants of ancient disintegrations we will never directly observe? The planet may have cycled through multiple ring systems across its 4 billion-year history, each one appearing, glittering, fading, and falling back into the clouds, replaced eventually by another. And then there are the gaps. Within the main ring structure, there are distinct dark bands, regions where ring particles are sparse or absent. The most dramatic of these is the Cassini division, a gap roughly 4,800 kilometers wide that separates the A ring from the B ring. When Herschel observed it in the 18th century, he believed the gap was empty. Modern observations show it is not quite empty. There is material there. It is simply much less dense than the main rings. And the reason it exists tells you something profound about the invisible architecture of gravity. Mimas, that small, battered, crater-covered moon, sometimes compared to the Death Star because of one enormous impact scar on its surface, is responsible for the Cassini division. Any particle that orbits in that gap would complete exactly 2 orbits for every 1 orbit of Mimas. That 2.1 resonance means Mimas tugs on those particles at the same point in their orbit every single time. The gravitational nudges accumulate. They push particles out of that orbital zone. They clear the gap, maintaining it across millions of years with mathematical precision. The rings of Saturn are not just beautiful, they are a living demonstration of orbital mechanics, gravitational resonance, and the laws of physics operating at a scale grand enough to see from Earth. Scientists soon discovered that similar resonances exist throughout the ring system, different moons clearing different gaps. The F-ring, a thin, twisted, braided strand of particles orbiting just outside the main rings, is actively shepherded by 2 small moons, Prometheus and Pandora, that orbit on either side of it. Prometheus passes inside the F-ring and pulls particles outward. Pandora passes outside and pushes particles inward. Together they confine the ring, maintaining its narrow structure, and as they do so they create gravitational waves, ripples in the ring that can be seen in images as a series of clumps, channels, and knots spiraling around the structure. The answer raised an even bigger question. If gravity and resonance can create this level of complexity in the rings, if the architecture of what looks like a simple flat disk turns out to be this intricate, this dynamic, this alive with invisible forces, what else is Saturn hiding in places we have barely begun to examine? The answer, as we will discover, is quite a lot. Travel north on Saturn. leave the ring plane behind, pass through the wispy outer atmosphere, descend into the thick bands of cloud that circle the planet in parallel ribbons of amber and cream, and keep going. Higher latitudes. The curvature of the planet becomes visible. The rings, seen from above, reveal themselves as an impossibly thin disk encircling the equator far below, their shadow cast in crisp geometric lines across the cloud tops. Keep going north, all the way to the pole, and there it is, a hexagon. Not a suggestion of a hexagon, not a rough approximation that a generous interpretation might call hexagonal. A near-perfect, six-sided geometric figure, each side approximately 13,800 kilometers long, each corner sharply defined, each angle almost exactly 120 degrees, spinning slowly around Saturn's North Pole at the same rate as the planet's deep interior. Each side of this hexagon is longer than the diameter of the entire Earth. The Voyager spacecraft photographed it in 1980 and 1981. Scientists looked at the images and, honestly, didn't quite believe what they were seeing. They thought it might be an artifact of the imaging process. A data glitch, something that would resolve itself into a normal-looking storm system on closer inspection. It didn't. When Cassini arrived at Saturn in 2004 and began returning images of incomparable quality, the hexagon was still there, still spinning, still maintaining its six-sided symmetry with the same precision that had been observed a quarter-century earlier. The storm had not shifted, had not drifted, had not degraded into a more typical oval or circular pattern. What happened next surprised researchers. Scientists measured the rotation rate of the hexagon's structure and found something unexpected. The hexagon itself, its geometric boundary, rotates at almost exactly the same speed as radio emissions from Saturn's deep interior. Those radio emissions are used as a proxy for the rotation of Saturn's core, the solid or semi-solid innermost layers that anchor the planet's rotation. The hexagon, in other words, is not just locked to the upper atmosphere. It appears to be anchored to something deep inside the planet. Something at the core. How? How does a geometric storm pattern at the surface of an atmosphere reflect the rotation of a planetary interior thousands of kilometers below? The short answer is that scientists are still working on it. Laboratory experiments have reproduced hexagonal vortex patterns by rotating two fluid layers at slightly different speeds and injecting them with the right turbulence, a kind of differential rotation that seems to produce six-sided structures under certain conditions. The mathematics of fluid dynamics can, under the right circumstances, generate standing geometric waves. But Saturn's hexagon has persisted for at least 45 years of direct observation. The atmospheric conditions that sustain it must be extraordinarily stable. On Earth, jet streams meander, shift, and break down over weeks or months. Saturn's north polar jet stream has been running the same hexagonal pattern for decades without significant change. And inside the hexagon? The interior of the hexagon contains a structure that is striking even by Saturn's unusual standards. At the very center, exactly at the North Pole, there is a massive rotating storm, a cyclone with a diameter roughly twice the size of Earth. Its eye is clear and crisp, surrounded by spiraling cloud walls reaching hundreds of kilometers into the atmosphere. Winds at the edge of the eye wall exceed 500 kilometers per hour. On Earth, polar cyclones are relatively common. Cold, slow-moving systems that develop in winter and dissipate in spring. They are driven primarily by temperature gradients between the polar region and lower latitudes, and they are not geometric. Saturn's North Polar Cyclone shows no sign of seasonal change. It has no winter to appear in and no spring to dissipate in. It sits exactly at the geometric pole, locked in place, spinning steadily, year after Saturnian year. The hexagonal jet stream and the polar cyclone together form a system of nested atmospheric structures, a hexagon containing a cyclone that has no parallel anywhere else in the solar system. Scientists soon discovered another layer to this mystery. The hexagon changes color with the seasons. Saturn's axial tilt is similar to Earth's, about 27 degrees, which means it experiences seasons. Saturnian seasons are long, very long. A full year on Saturn takes approximately 29.5 Earth years, which means each season lasts over 7 years. When Cassini arrived at Saturn, the North Pole was in deep winter, turned away from the sun, plunged into a darkness that would last years. The hexagon was a deep bluish color, visible in ultraviolet and near-infrared images. As the mission progressed and Saturn moved toward northern spring, then northern summer, something changed. The hexagon grew warmer. The upper atmospheric chemistry shifted, and the hexagon turned gold. A warm amber gold, matching the banded clouds of lower latitudes where sunlight had been falling for decades. The pole was catching up to the chemistry of a sun-warmed world, and the hexagon was changing with it, its color shifting over the years of Cassini's observations from cool blue to warm gold. Cassini tracked this transition in real time. Scientists watched a planetary structure the size of a continent change color across years of observation. And with that color change came an understanding. The atmosphere inside the hexagon was being photochemically altered by sunlight. New molecules were forming. Hazes were thickening. The hexagon was not just a dynamic geometric form. It was a complex chemical environment that evolved with Saturn's seasons. But that wasn't the strangest part. Even as scientists developed models to explain the hexagon's shape and behavior, an underlying question remained unanswered. Why does Saturn have a hexagon at its north pole, but not its south? The South Pole has a cyclone. It has storms. It has interesting atmospheric dynamics. But it does not have a hexagon. No six-sided structure has been observed at the South Pole. Why the asymmetry? If the same physics that produces the hexagonal pattern at the north operates uniformly across the planet, why doesn't the South reflect it? Some researchers suggest that the hemispheric difference might be related to where Saturn currently is in its orbit. In recent history, Saturn's north pole has been slightly farther from the Sun during parts of the year than the South, a consequence of the planet's slightly elliptical orbit. But the difference is small, and whether it is sufficient to explain the total absence of a southern hexagon remains an open question. Others have proposed that the hexagon might be connected to some asymmetric feature in Saturn's interior, some structural difference between the two hemispheres deep inside the planet that is not reflected at the surface in any observable way. But no one has direct evidence for this. It remains speculation. What happened next surprised researchers in the Cassini team. In 2017, during Saturn's northern summer, the first northern summer that had been observed since the Voyager flybies, scientists began to see new features developing inside the hexagonal boundary. Small, transient vortices forming and dissolving within the main jet stream. Thin filaments of cloud threading between larger structures. The hexagon was not static, it was breathing. And then the mission ended. In September 2017, Cassini, out of fuel, its mission complete after 13 years of extraordinary science, was guided deliberately into Saturn's atmosphere. It entered the clouds traveling at over 113,000 kilometers per hour. It burned. It fragmented. Within a few minutes, the spacecraft that had transformed our understanding of Saturn was gone, consumed by the planet it had spent so long studying. The hexagon spins on. Whatever its secrets, they are still up there, turning, patient waiting for the next spacecraft bold enough to come and ask, "Of all the moons in the solar system, there is one that stands apart, not because of its size, though it is enormous, larger than the planet Mercury, not because of its appearance, though that appearance is haunting and strange, but because of what it shares with Earth, not rocks, not craters, not the basic mineral chemistry of a rocky body, weather, real weather, not the ghost of weather, not the remnants of something that once existed, active, current, right now weather, clouds forming and dissipating, precipitation falling from the sky, rivers and lakes and seas filled with liquid, a thick atmosphere, dense enough to support weather systems, to have wind patterns, to create haze and smog and rain. This is Titan, Saturn's largest moon, the second largest moon in the solar system, and one of the strangest places we have ever looked at. From space, Titan is invisible. That orange haze, a thick photochemical smog produced by ultraviolet radiation interacting with nitrogen and methane in the upper atmosphere, completely obscures the surface. When Voyager flew past in 1980, its cameras saw nothing but an orange sphere, a uniform, featureless ball of murk, revealing nothing of what lay beneath. Scientists knew there was a surface. They just couldn't see it. That changed in 2004 when Cassini arrived and began using radar, infrared imaging, and other instruments capable of penetrating the haze. And in January 2005, when the Huygens probe, a small lander carried to Saturn by Cassini and released to descend through Titan's atmosphere, transmitted images during its 2.5-hour descent and brief time on the surface. What those instruments revealed was astonishing. Titan has mountains. It has plains of frozen water ice covered in organic compounds that give the landscape a dark, brownish hue. It has drainage channels, branching, dendritic networks carved into the landscape by liquid flowing downhill, exactly as river systems on Earth carve their way toward the sea. Those channels lead to lowland areas, broad flat regions where radar reveals smooth surfaces and low reflectivity, the hallmarks of liquid, lakes, seas, large bodies of standing liquid on the surface of a world nearly 1 billion miles from the sun. But here is what makes Titan so fundamentally different from anything in our immediate experience. The liquid in those lakes and seas is not water. It cannot be water. At Titan's surface temperature of approximately -179 degrees Celsius, water is rock-hard frozen. It is part of the landscape, a geological mineral, not a fluid. The liquid filling Titan's seas and lakes and rivers is methane. Liquid methane, the same substance we use as natural gas. Ethane, too, another simple hydrocarbon. On Titan, the role that water plays in shaping Earth's surface is played by methane, cycling through the same phases, evaporating from the surface, rising into the atmosphere, forming clouds, precipitating back down as methane rain. Scientists soon discovered that this methane cycle is not just chemically interesting, it is geologically powerful. The methane rain on Titan falls in enormous quantities during seasonal storms, filling rivers that carve channels into the icy landscape, transporting material to the sea basins, depositing organic sediment, building deltas and alluvial fans that Cassini's radar captured in extraordinary detail. There is a sea at Titan's North Pole called Kraken Mare, named for the legendary sea monster. That is larger than the Caspian Sea on Earth. Hundreds of kilometers across, filled with liquid methane and ethane, bounded by low shorelines that change shape over the Saturnian year as evaporation and rainfall shift the balance between liquid input and liquid loss. And this is where things become even more fascinating. On Earth, the carbon in our atmosphere is locked into a cycle. Carbon dioxide is absorbed by plants, which are eaten by animals, which eventually decompose and return carbon to the atmosphere or the rocks. It is a closed loop that has kept Earth's chemistry roughly in balance for hundreds of millions of years. On Titan, methane plays a similar role. It cycles through the atmosphere, the surface, and back, but there is a profound problem with this analogy. Methane on Titan is being destroyed. Ultraviolet radiation from the sun breaks methane molecules apart in the upper atmosphere. The products of that reaction become part of the orange haze, complex organic molecules called tholins that fall slowly to the surface and accumulate over geological time. The process of converting methane to haze is one way. The methane is being consumed. If Titan's methane is being steadily destroyed, and if the current amounts of methane in the atmosphere and surface would be depleted on a timescale of around 30 million years, then where did the methane come from? Something must be replenishing it. Comets? Subsurface reservoirs? An internal geological source releasing methane from within Titan's interior? Scientists have proposed all of these options. None has been definitively confirmed. But the question raises a possibility that makes scientists genuinely excited. What if Titan's methane is being replenished biologically? On Earth, much of the methane in our atmosphere is produced by microorganisms. Methanogenic archaea, ancient single-celled organisms that consume hydrogen and produce methane as a metabolic byproduct, are responsible for a significant fraction of Earth's methane flux. What if something similar operating on entirely different chemistry is doing the same thing on Titan? What if there are organisms in Titan's lakes, organisms that breathe hydrogen instead of oxygen, eat organic molecules raining down from the atmosphere, and exhale methane, quietly maintaining the cycle? This is not a fringe idea. It is a legitimate scientific hypothesis, taken seriously by astrobiologists, that has driven mission proposals and theoretical work. Carl Sagan and colleagues proposed in 1984 that Titan's chemistry might support life. In 2010, researchers published papers suggesting that if hydrogen-consuming life existed on Titan's surface, it would produce measurable depletions of hydrogen near the surface, and that this is in fact what the data shows. The hydrogen near Titan's surface is less abundant than atmospheric models predict it should be. Does this prove life exists on Titan? Absolutely not. There are abiotic explanations for the hydrogen depletion, but the data is consistent with life. The door is not closed. And the answer raised an even bigger question, which is whether we are looking at Titan's surface for the right kind of life. If life exists there, it would be so chemically alien, so completely different from anything on Earth, that we might not recognize it with instruments designed for familiar biochemistry. NASA is sending a spacecraft to find out. The Dragonfly mission, a rotorcraft lander, a drone the size of a large car, is scheduled to reach Titan in 2034. It will fly through Titan's thick atmosphere on electrically powered rotors, landing at multiple sites across the surface, sampling soil and atmosphere, looking for the chemical signatures of life or prebiotic chemistry. It will travel more across Titan's surface than all of Earth's Mars rovers combined, covering hundreds of kilometers, visiting locations from open plains to the edges of lakes to the central peak of a large impact crater called Selk, where the heat of the impact would have temporarily melted Titan's icy crust and mixed it with organic compounds, creating a warm, wet, chemically rich environment that might have persisted long enough for interesting chemistry to occur. Dragonfly is one of the most ambitious planetary science missions ever approved. Its target is one of the strangest worlds we have ever observed. And in the 2030s, it will begin to answer questions that have been building since Galileo first turned his telescope towards Saturn more than 400 years ago. But Titan, extraordinary as it is not even Saturn's most compelling moon for the search for life. For that, we need to travel to a world that looks, at first glance, completely unremarkable. A small, pale, quiet moon, orbiting in the faint outer regions of Saturn's ring system. A moon that is, on its surface, utterly silent. And beneath that surface, erupting, Enceladus is not a dramatic-looking world. It is small, just over 500 kilometers in diameter. Small enough that you could drive across it in a few hours at highway speed. It is smooth, mostly, with a surface of nearly pure water ice that reflects nearly 99% of the sunlight that strikes it, making it one of the most reflective bodies in the solar system. From a distance, it looks almost like a pristine white ball. Quiet, still, cold, Voyager flew past it and found it interesting, but not spectacular. There were hints of a young, active surface, regions with very few craters, suggesting the landscape had been reshaped relatively recently. But the resolution wasn't sufficient to tell what was actually going on. Then Cassini arrived, and on February 17, 2005, it made its first close flyby of Enceladus, and everything changed. The spacecraft's instruments detected something that shouldn't have been there. Vapor, water vapor, erupting from the southern pole of this small, cold moon in towering plumes that reached hundreds of kilometers above the surface before dispersing into space. The South Polar region, which should have been the coldest part of an already frigid moon, was warm, anomalously warm. Cassini's heat sensors detected a thermal signature at the South Pole that was wildly inconsistent with what the surrounding environment predicted. And where the plumes were erupting, there were cracks. Long, roughly parallel fractures in the ice, each approximately 130 kilometers long and 500 meters deep, separated from one another by regular spacing, running in near parallel lines across the south polar terrain. They have a blue-green color in enhanced images, older ice compressed and clarified by geological stress, and they are now known as the tiger stripes. They are the origin point of Enceladus's plumes, the source vents through which water and ice and gas erupt from deep within the moon. Scientists soon discovered that the plumes of Enceladus are not just water. They contain sodium chloride, salt, table salt, the same compound that makes Earth's oceans salty. Finding salt in the plumes immediately implied a liquid ocean in contact with a rocky seafloor, because salt at those concentrations is characteristic of water that has been in prolonged contact with rock, dissolving minerals over geological time. The plumes contain molecular hydrogen gas, produced by a specific process, the reaction of water with hot rock in the presence of catalytic minerals. This process, called serpentinization, occurs on Earth at hydrothermal vents on the ocean floor, where seawater percolates down into the hot oceanic crust and reacts with certain minerals. It produces hydrogen as a byproduct, and hydrogen is an energy source. It is the fuel that sustains entire ecosystems at Earth's hydrothermal vents. Communities of organisms that live in complete darkness, without sunlight, powered entirely by the chemical energy of hot, mineral-rich water. The plumes contain carbon dioxide. They contain methane. They contain a suite of organic molecules, not the complex biology-derived organics, but the simple building blocks, amino acid precursors, fatty acid analogs, ring compounds, the raw material of chemistry that, under the right conditions, can organize into something more complex. And the silica nanoparticles. Perhaps most telling of all, Cassini detected silica nanoparticles of a very specific size in Saturn's E-ring, which is the faint, diffuse ring maintained by material from Enceladus's plumes. These particles could only form at temperatures above 90 degrees Celsius, in water with a specific, slightly alkaline chemistry. Their size is consistent with formation in a hydrothermal vent environment on a rocky seafloor. Enceladus has a global liquid ocean. It has been confirmed by multiple independent lines of evidence, including precise measurements of the moon's gravitational wobble during Cassini flybies that could only be explained by a liquid layer beneath the ice. The ocean is deep, possibly 30 to 40 kilometers deep in some regions, and lies beneath an ice shell that varies in thickness from a few kilometers in the South Polar region to tens of kilometers elsewhere. At the South Pole, the ice is thin enough that the pressure from the ocean below forces water upward through the tiger stripe fractures. The water rises, flashes to vapor in the near vacuum above the surface, and erupts into space in those tall, graceful plumes that Cassini photographed with such clarity that they look, in the images, like a living thing breathing. And the bottom of that ocean is hot, rocky, chemically active seafloor, in contact with liquid water, producing hydrogen and organic molecules, maintaining temperatures and chemistries that sustain one of the most productive ecosystems on Earth, the hydrothermal vent communities, for billions of years. The question of life on Enceladus is not a philosophical abstraction. It is a specific, testable, scientifically concrete question Is there life in this ocean? The answer matters enormously. If there is, if even microbial life exists in the warm, dark waters of Enceladus's interior, it would be the most important discovery in the history of science. It would mean that life is not a singular miracle unique to Earth. It would mean that wherever liquid water, energy, and chemistry exist in the right combination, life follows. And given how common those conditions appear to be, not just in our solar system but throughout the galaxy, the implications would transform our understanding of the universe and our place in it. What happened next surprised researchers who were planning the follow-on science. Scientists realized that Enceladus's plumes are not just evidence of what might be inside the moon. They are samples of what is inside the moon. The water erupting into space is ocean water. It has been inside the moon. It has been in contact with the seafloor, with whatever chemistry or biology exists down there. And Cassini flew through those plumes, directly through them, multiple times, its instruments sampling what the plumes carried. What Cassini found in those plumes we have catalogued. What Cassini may have missed, because it wasn't designed to detect life directly, wasn't equipped with the biosignature detection instruments that a purpose-built mission would carry, is the central question that drives the next generation of mission planning. A follow-on mission to Enceladus, one with mass spectrometers tuned to detect amino acids, cell membrane analogs, lipid biomarkers, and other signs of biological chemistry, could potentially fly through the plumes and sample them directly. The ocean of Enceladus is bringing its contents to us, ejecting them into space. We don't even need to land. We just need to fly through the plume with the right instruments. The answer is there, drifting in space, 886 million miles from Earth, waiting to be caught. And the question it carries is perhaps the oldest question human beings have ever asked. Are we alone? Let us go somewhere no spacecraft has ever gone. Let us go inside Saturn. The planet's upper atmosphere is where we have spent most of our observational time. The bands of clouds, the hexagon, the storms, the regions where Cassini's cameras could see. But the atmosphere is just the outermost layer, the thin skin on a vast interior that makes up the overwhelming bulk of the planet's mass. What lies beneath those clouds? The first thing you would encounter, descending below the visible cloud deck, is simply more atmosphere. Cloud layers at different altitudes, composed of different materials, water ice clouds deep and cold, ammonium hydrosulfide clouds above that, ammonia ice clouds near the top. Each layer at a different pressure and temperature, each with its own chemistry and dynamics. The deeper you go, the hotter it gets. The pressure rises steadily. At some depth, perhaps a few hundred kilometers below the cloud tops, the atmosphere becomes dense enough that the distinction between gas and liquid begins to blur. You are not descending through gas into liquid, as you would entering an ocean on Earth. You are in a gradual transition, a region where the pressure has squeezed the atmosphere so intensely that it takes on properties somewhere between. Supercritical hydrogen, a state of matter that doesn't behave quite like anything familiar. Continue deeper. The pressure continues to rise. Tens of thousands of atmospheres. Hundreds of thousands. And then, at a depth still far from Saturn's core, something extraordinary happens. the hydrogen becomes a metal. Not solid metal, not the kind of metal you could hold in your hand, but metallic in the physical sense, a conductor of electricity. When the pressure reaches approximately 1 to 2 million atmospheres, hydrogen, which in everyday conditions is a colorless, barely reactive gas, undergoes a phase transition into a state called metallic hydrogen, where the electrons are no longer bound to individual atoms, but flow freely through the material, exactly as they flow through the copper in a wire. Metallic hydrogen is a theoretical substance that has fascinated physicists for nearly a century. On Earth, we have only ever created it for fractions of a second in extreme laboratory experiments, tiny samples subjected to pressures far beyond anything achievable in sustained conditions. In Saturn's interior, it makes up the bulk of the planet's mass, existing in vast volumes at sustained pressures for billions of years. And because metallic hydrogen conducts electricity, and because Saturn is rotating, this enormous conducting fluid acts like a dynamo. It generates Saturn's magnetic field, one of the largest and most powerful in the solar system, extending millions of kilometers into space in a vast magnetosphere that traps charged particles, creates radiation belts, and interacts dynamically with the solar wind. Scientists soon discovered something about Saturn's magnetic field that is profoundly strange. Every other planetary magnetic field we know of is offset. Earth's magnetic poles don't align perfectly with its geographic poles. The magnetic North Pole is currently in the Canadian Arctic, several degrees away from true north, and it wanders. Jupiter's magnetic field is tilted by about 10 degrees from its rotation axis. Uranus and Neptune have wildly tilted magnetic fields. The physics of planetary dynamos, the mathematical models we use to understand how rotating conducting fluids generate magnetic fields, predicts that some degree of tilt is normal. Expected, almost required. Saturn's magnetic field is aligned to within 1 degree of its rotation axis, maybe less. It is almost perfectly symmetric around the rotation pole, showing no significant offset, no tilt, no departure from axial symmetry that our instruments can measure. This is, mathematically speaking, almost impossible. Dynamo theory says that a perfectly axis-symmetric magnetic field cannot be sustained. It is related to a mathematical result called Cowling's theorem, a fundamental result in magnetohydrodynamics that essentially proves that axisymmetric dynamos are not self-sustaining. And yet there is Saturn, with a nearly perfect axisymmetric field, spinning away for billions of years. Something must be breaking the symmetry somewhere. Something in Saturn's interior must be introducing some small but significant departure from perfect symmetry that allows the dynamo to operate. But whatever it is too small or too deep for our instruments to detect directly. One compelling hypothesis involves the helium rain. Saturn, like Jupiter, formed primarily from hydrogen and helium, the two most abundant elements in the universe. But as the planet cooled over billions of years, the helium in its outer metallic hydrogen region began to condense into droplets, like rain forming in a cloud. These helium droplets fall inward toward the planet's deeper regions, releasing gravitational energy as they go, and this process provides a significant fraction of the excess heat that Saturn radiates. Saturn emits about twice as much energy as it receives from the Sun, and helium rain is a major contributor to that energy budget. But helium rain does more than generate heat. The falling helium droplets interact with the metallic hydrogen in complex ways, potentially creating layered regions of slightly different conductivity and fluid properties. Some researchers believe that a thin, stable layer of non-metallic hydrogen just above the metallic region, a layer where helium rain creates a sharp compositional gradient, could be the key to explaining Saturn's anomalously symmetric magnetic field. This stable layer might be filtering the magnetic field, smoothing out asymmetries as they are generated, producing the nearly perfect alignment we observe. But this is still a theoretical framework. Direct evidence from Saturn's interior is not obtainable with current technology. We cannot send a probe to the pressures where metallic hydrogen exists. We cannot sample the helium rain. We are reasoning from the outside in, using magnetic field measurements, gravity data, oscillations in Saturn's rings caused by internal density waves, and theoretical models to piece together a picture of a place we will never directly observe. And it raises yet another question. If Saturn's interior is generating heat through helium rain, a process that has been ongoing for billions of years, when did it start? And will it eventually stop? As the helium becomes fully separated and settled into deeper regions, the supply of falling droplets that generates heat will dwindle. What happens to Saturn when that heat source exhausts itself? What does Saturn become as it slowly cools toward the equilibrium temperature of a body far from the Sun? The answer raised an even bigger question. Saturn is young in some ways and ancient in others. Its rings are younger than the dinosaurs. But its interior has been running the same slow, inexorable physical process for billions of years. The planet is simultaneously changing rapidly at its surface and at its core evolving with geological slowness that makes human timescales irrelevant. Saturn's interior is a world unto itself, a world of extreme physics where the rules familiar from everyday experience break down entirely and matter behaves in ways that require new mathematics to describe. It is perhaps the least accessible part of Saturn, and perhaps the most important for understanding how giant planets like Saturn form, evolve, and ultimately end. Saturn is a planet defined by its storms, not in the chaotic, unpredictable way of a weather system on Earth, constantly shifting and evolving in response to local conditions. Saturn's storms have rhythms, cycles, patterns that repeat across decades, suggesting that whatever drives them is deeply embedded in the planet's atmospheric dynamics. Not random, not accidental, but systematic. The most dramatic of these recurring events is called the Great White Spot, or more precisely, the Great White Oval, because it begins as an oval-shaped brightening in Saturn's cloud bands, an eruption of brilliant white cloud material against the muted amber background of the surrounding atmosphere. They appear approximately every 30 years, 1876, 1903, 1933, 1960, 1990, 2010. Not exactly every 30 years, the intervals vary somewhat, but with a regularity that is striking and that must reflect some periodic process in Saturn's interior or atmospheric dynamics. And 30 years, not coincidentally, is approximately the length of a Saturn year. The giant white spot events appear to be tied to the planet's annual cycle, appearing preferentially during northern hemisphere summer, when the northern regions receive maximum solar heating. But the scale of these events is difficult to convey in ordinary language. The 1990 Great White Spot was observed by the Hubble Space Telescope just months after its launch, and it became one of the most striking images of Hubble's early career. The eruption began as a small, bright area at Saturn's equator and expanded rapidly. Within weeks, the bright cloud material had spread to encircle the entire planet, a complete band of white that wrapped all the way around Saturn's equatorial region. The storm was not just large, it was planetary, a disturbance that affected the entire global atmosphere. The 2010 event was even more powerful. It began in December 2010 in the Northern Hemisphere, and Cassini was in an ideal position to observe it in unprecedented detail. What the spacecraft saw was extraordinary. The initial eruption was a single bright spot, a thunderstorm of almost incomprehensible scale, a convective plume punching upward through the atmospheric layers at speeds of hundreds of meters per second, driven by the condensation of water and ammonia releasing their latent heat, exactly as thunderstorms on Earth are powered by rising warm air, releasing heat as water vapor condenses. But on Saturn, the scale is different in every dimension. The initial plume, Cassini measured, was releasing energy equivalent to the simultaneous detonation of hundreds of millions of nuclear weapons. The convective plume spread outward in both directions along the latitude band, developing into a circumplanetary belt of turbulent, mixed atmosphere that eventually stretched to encircle the entire planet. The storm ran for approximately 8 months before finally dissipating. During that time, it generated vortices, wave patterns, and turbulent structures that were tracked by Cassini's cameras in daily imaging sequences. Scientists soon discovered something unexpected in the storm's aftermath. The stratosphere above the storm site was dramatically heated. Not by the storm itself directly, but by the waves the storm generated, massive acoustic waves propagating upward from the troposphere into the stratosphere, depositing energy, raising temperatures in a region that should not have been affected by convection in the deep clouds below. The temperature anomaly in Saturn's stratosphere, measured by Cassini's thermal instruments, was dramatic, tens of degrees above the expected values, and it persisted for years after the storm's visible surface activity had ended. The storm had reached up and permanently altered the chemistry of Saturn's upper atmosphere. New molecules formed in the stratosphere under the abnormal temperature and energy conditions. The storm's signature was written into the planet's chemical composition in ways that were still detectable years later. And this is where things become even more fascinating. Why every Saturn year? Why does the atmospheric stability hold for 29 or 30 years and then suddenly, dramatically collapse? What accumulates over one Saturnian year that eventually becomes unstable enough to trigger a global event? The leading hypothesis involves the seasonal cycle. During the long Saturnian year, solar heating differentially warms the northern and southern hemispheres as they take turns facing the sun. This drives slow, global circulation patterns that accumulate moisture, or rather its Saturnian equivalent, water vapor and ammonia, in specific atmospheric layers. Over decades, this accumulated material becomes increasingly unstable. The layer becomes like a coiled spring. Any small perturbation, a localized wind shear, a temperature fluctuation, can trigger a convective eruption that releases the accumulated energy in a single catastrophic event. But the mechanism has never been definitively confirmed. The models reproduce some features of the observed storms, but not all. And the 30-year periodicity, why it should track so closely with the Saturn year, why Northern Hemisphere summer should be the triggering condition, why the events should be so geographically focused, remains partially unexplained. What happened next in the 2010 storm surprised even the most experienced Saturn researchers. The expanding tail of the storm, the long streamer of turbulent clouds that developed in the wake of the initial eruption and wrapped eastward around the planet, eventually circled all the way around and met the original storm head. When the tail reached the original eruption point, the two systems interacted. The fresh convective energy of the eruption met the turbulent, mixed atmosphere of the aging tail, and the interaction generated a new eruption, a secondary brightening, a fresh explosion of cloud material, visible in Cassini's images as a second bright spot emerging from the collision zone. The storm was feeding itself. The mechanism that had triggered it was being reinforced by the storm's own dynamics. And then, as abruptly as it had amplified, it began to decay. The secondary eruption faded. The bright clouds dispersed. Within months, the planet's banded structure reassembled, and Saturn returned to its characteristic appearance: calm, golden, ringed, beautiful. The spring will coil again. In approximately 2040, if the pattern holds, another great white spot will erupt. Somewhere in Saturn's northern hemisphere, a thunderstorm of planetary scale will begin, and the atmosphere of the most beautiful planet in the solar system will convulse. But by then, Cassini will be gone. Whatever mission flies to Saturn in the 2040s, whoever builds it and names it and sends it across the void will witness the next storm with instruments we have not yet designed. What they find will surely raise questions we haven't yet thought to ask. Saturn does not have one moon, or two, or a handful. As of the most recent count, Saturn has 146 confirmed moons. 146 individual worlds of vastly different sizes, compositions, ages, and personalities, orbiting a single planet. Jupiter has more massive moons, but Saturn has more moons overall. The outermost ones are small, irregularly shaped captured objects, ancient asteroids, or Kuiper belt bodies that wandered too close to Saturn's gravity and were caught settling into distant, inclined, often retrograde orbits. Many of them are probably fragments of larger bodies that were broken apart in ancient collisions. They orbit so far from Saturn that a single orbit takes years, and they are so small that they were only discovered using modern large telescopes and sensitive cameras. But the inner moons, the ones close to Saturn, interacting with the ring system, shaped by the planet's powerful gravity, are where the real stories live. We have already spent time with Titan and Enceladus. But there are others, Mimas, the Death Star moon. Its most striking feature is the Herschel crater, an impact scar roughly 130 kilometers in diameter on a moon only 400 kilometers across. Whatever struck Mimas to create Herschel came very close to shattering the moon entirely. The impact must have sent catastrophic shockwaves through the entire body, and the fact that Mimas survived at all suggests it is more structurally resilient than it appears. Mimas is significant not just for its dramatic appearance, but for its gravitational role, it maintains the Cassini division in Saturn's rings, a subtle but significant influence on the ring structure that has persisted for millions of years. Yet another mystery emerged from Mimas recently that has researchers genuinely puzzled. Mimas wobbles. Not the entire moon, but its rotation. It rocks slightly back and forth in a way that should not be possible if the moon is a simple, uniform ball of ice. The wobble was measured precisely by Cassini. The pattern of that wobble, technically called a libration, is consistent with either an elongated, irregularly shaped rocky core or a global liquid water ocean beneath the ice. Scientists looked at the libration data and found that the magnitude of the wobble is best explained by an ocean. A hidden ocean inside Mimas, a moon that shows no surface signs of the kind of geological activity associated with Enceladus's ocean. No tiger stripes, no plumes, no anomalous heat. If Mimas has an ocean, it is a new ocean. Very young, geologically speaking, perhaps formed in the last 10 to 25 million years as tidal forces from Saturn heated the interior beyond the melting point of ice. The surface ice, still cold and undeformed, shows the old topography of a moon that was once uniformly frozen. The ocean beneath has not yet had time to deform the surface. It has not yet had time to melt the ice from below and produce the kind of geological expressions that tell us Enceladus is active. Mimas is Enceladus before Enceladus knew it was Enceladus. An ocean world in its infancy. Scientists soon discovered that this has profound implications. If Mimas's ocean is only tens of millions of years old, and if Enceladus's activity has been ongoing for hundreds of millions of years, then there may be a progression, a life cycle of ocean moons, in which tidal heating creates an ocean. That ocean evolves chemically over time, and the moon transitions from a quiet, apparently inert body to an active, erupting world. Mimas may be showing us what Enceladus looked like before it became what it is today, and Enceladus may be showing us what Titan's subsurface history looked like before Titan evolved its methane cycle. There is a story across these moons, a connected narrative of formation and evolution, tidal heating and chemical development, that links Saturn's diverse family of worlds into something more coherent than a random assortment of icy bodies. Iapetus deserves a moment. The two-toned moon. Cassini Gian Domenico himself, the astronomer who discovered the Cassini division, also discovered Iapetus in 1671 and immediately noticed something bizarre. The moon was visible only on one side of Saturn and invisible on the other. He correctly deduced that one hemisphere of Iapetus was much darker than the other, and the moon kept the same face towards Saturn as it orbited, diidally locked, as our own moon keeps the same face toward Earth. So when the dark hemisphere faced toward Earth, the moon was too faint to see. Close-up images from Cassini revealed the extent of the dichotomy. The leading hemisphere of Iapetus, the one that faces the direction of travel in its orbit, is covered in a dark reddish-brown material as black as coal. The trailing hemisphere is nearly as white as fresh snow. The contrast is stark and alien-looking, like a moon that was painted half and half. What caused the dichotomy remains, even after Cassini, not completely settled. Dust from outer moons falling preferentially onto the leading hemisphere, darkening the ice over time, combined with a thermal process where sunlight causes dark material to migrate from warmer equatorial regions to colder polar areas, creating self-reinforcing patterns of dark and light. The leading hemisphere gathers dust. The dust absorbs more sunlight. The ice sublimates from the warmer dark regions. The water vapor refreezes in colder areas. The contrast grows over time. But the extreme mountains of Iapetus, a 20-kilometer high equatorial ridge that runs almost perfectly along the equator like a seam on a ball, have never been satisfactorily explained. Some form of ancient rapid rotation, internal convection in the early moon, impact debris settling along the equatorial plane. No single hypothesis has won consensus. Then there's Hyperion, chaotically tumbling through space, not rotating in a stable way but tumbling irregularly, never settling into a fixed orientation. Covered in a deep, spongy-looking surface of craters that are unusually deep and regular, giving it the appearance of a cosmic sea sponge. Phoebe, a captured object from the outer solar system, dark and ancient, orbiting Saturn in the retrograde direction far from the main moon family, its composition more like a Kuiper belt object than a Saturnian moon. Its surface dated to the earliest era of the solar system. It is a piece of primordial outer solar system material that was captured by Saturn's gravity billions of years ago and has been orbiting in distant solitude ever since. And the small inner moons that live within and around the ring system itself, Pan, orbiting within the Encke gap. Its equatorial ridge raised by ring material settling onto its surface, Daphnis, a tiny moon orbiting within the Keeler gap, its gravity raising waves in the ring edges as it passes, waves that Cassini photographed in extraordinary detail. 146 moons, each one a world, each one carrying its own questions, and each one embedded in a system of gravitational interactions, compositional relationships, and historical connections that weaves them together into a coherent but still partly mysterious story. The answer raised an even bigger question. Was this family always this large? Did Saturn always have 146 moons? Or did some of those moons used to be larger bodies, perhaps a single large moon, torn apart by tidal forces or shattered in a collision, whose fragments now orbit as the irregular outer moons we count today? Some researchers believe the rings and several small inner moons share a common origin, the disruption of a large, icy inner moon that wandered too close to Saturn and was destroyed, perhaps as recently as 100 million years ago. Its debris forming the rings we see today, and the small inner moons built from ring material that accumulated over time. If so, then Saturn's family is not static. It is still evolving, still assembling, still becoming whatever it will be in 100 million years. There was a spacecraft that fell in love with Saturn. That is not a scientific statement. It is not the kind of language that appears in peer-reviewed papers or mission reports. But it captures something true about the relationship between the Cassini mission and the planet it orbited for 13 years. Because the data that mission returned, the images, the measurements, the discoveries, has the character of intimate knowledge. The kind of knowledge you only gain by staying. Cassini launched in October 1997 and arrived at Saturn in July 2004 after a 7-year journey that included gravity assist flybys of Venus, Earth, and Jupiter. It entered Saturn orbit by firing its main engine for nearly 97 minutes to slow down enough to be captured by Saturn's gravity, a burn that, if it had failed, would have sent the spacecraft past Saturn and into interstellar space with no possibility of recovery. The burn succeeded, and what followed was one of the most productive planetary science missions in history. Over 13 years, Cassini completed 294 orbits of Saturn. It conducted 162 targeted flybys of Saturn's moons. It released the Huygens probe that descended through Titan's atmosphere and landed on its surface. It discovered the plumes of Enceladus. It mapped the surfaces of more than a dozen moons in detail. It measured Saturn's magnetic field, tracked its storms, watched its seasons change, observed the rings at close range in every configuration the orbital geometry allowed. It returned more than 500 gigabytes of data, over 450,000 images. More than 3,000 scientific papers have been published using Cassini data. The mission fundamentally transformed our understanding of Saturn and will continue generating scientific discoveries for decades as researchers continue analyzing the dataset. But the discoveries that came in the final years of the mission, during what NASA called the grand finale, were among the most significant of all. Scientists soon discovered something about Saturn's interior that no earlier measurement had been able to determine. In the final months of the mission, Cassini executed a series of orbits called the ring-grazing orbits, where it passed just outside the rings, closer to Saturn's outer ring edge than it had ever been. Then, in the final weeks, it executed the grand finale orbits, 22 passes between the innermost ring and the top of Saturn's atmosphere, through a gap only a few thousand kilometers wide, threading the needle between the rings and the planet at speeds exceeding 100,000 kilometers per hour. In this region, Cassini was able to measure Saturn's gravity with a precision that had never been achievable before. And those gravity measurements revealed something surprising about the planet's interior structure. The deep interior of Saturn is not the simple, smoothly varying structure that models had assumed. There are density variations, regions of different composition or temperature, that create gravitational anomalies detectable in the spacecraft's trajectory. Interpreting those anomalies requires complex modeling, but the data suggests that Saturn's deep interior may be more like a fuzzy core, a region where rocky and icy material and metallic hydrogen are not cleanly separated into layers, but instead blurred together, with no sharp boundary between core and envelope. This has implications for how Saturn formed. Clean, layered interior models suggest a planet that grew by first accumulating a solid core of rock and ice, then sweeping up hydrogen and helium from the surrounding protoplanetary disk. A fuzzy, mixed interior suggests a more chaotic formation process, perhaps rapid accretion where material was mixed as it accumulated, or subsequent erosion of a once sharp core boundary by convective mixing over billions of years. The grand finale also provided measurements inside the rings, the first direct measurements of ring material from within the gap between the rings and the planet. Before the grand finale, everything we knew about the ring particle environment was inferred from outside. Now, for the first time, Cassini's instruments were sampling the ring particles, measuring the dust and gas directly, collecting atoms and molecules from the ring material, and feeding them into the spacecraft's mass spectrometers. The rings were contributing organic molecules to Saturn's upper atmosphere. Carbon-bearing compounds, water, even small organic molecules were flowing from the rings downward into the planet at rates that exceeded previous estimates. The rings are not just structurally dynamic, they are chemically feeding the planet they orbit. Saturn is slowly consuming its own rings, incorporating their material into its upper atmosphere and clouds. What happened next surprised the entire mission team. The magnetic field measurements inside the gap between the rings and the planet showed that the field's near-perfect alignment with the rotation axis is even more precise than the best previous measurements had indicated. Whatever mechanism is producing this anomalous symmetry is operating with extraordinary precision, far more precisely than theoretical models easily explain. And inside the gap, the magnetic field showed complex small-scale structures, fluctuations at scales much smaller than earlier measurements could resolve. These fluctuations are themselves carrying information about Saturn's interior, about the structure of the metallic hydrogen region, about the dynamics of the conducting fluid deep inside the planet. Analysis of these small-scale variations is ongoing, and researchers believe it may eventually provide the most detailed picture of Saturn's interior ever assembled from external measurements. On September 15, 2017, the grand finale ended. The team had made the decision years earlier. When the mission concluded, Cassini would not be allowed to drift derelict in Saturn's system, where it might eventually collide with Titan or Enceladus and contaminate them. Possibly contaminate ocean worlds that might harbor life, with Earth microbes that had survived the journey. Instead, it would be directed into Saturn itself. The spacecraft made its final maneuver. It aimed itself at the planet's atmosphere. At 6:31 in Pacific time, signal from Cassini was lost. The spacecraft had entered Saturn's atmosphere, traveling so fast that it was immediately engulfed in superheated plasma, its structure ablating and fragmenting. Within minutes, there was nothing left. The atoms that had comprised Cassini, the metals, the electronics, the materials built by human hands across multiple continents were dispersed into Saturn's clouds. In some sense, Cassini is still there. Its atoms are somewhere in Saturn's vast atmosphere, slowly mixing downward, eventually becoming part of the planet itself. The mission that studied Saturn for 13 years was absorbed by it at the end. It became Saturn. The team that had built and operated the mission gathered to watch the final signal. Many of them had dedicated decades of their careers to Cassini. Some had spent their entire professional lives on it. When the signal ended, there was silence in the mission control room at the Jet Propulsion Laboratory. Then applause and tears. It was not grief, exactly. It was something more complex. The pride of completion. The melancholy of endings. The knowledge that what they had done was extraordinary, and that even though the spacecraft was gone, the science it had generated would continue for generations, and the understanding that somewhere, 886 million miles away, Saturn was still turning, still ringed, still storming, still hiding its secrets, still waiting for whoever comes next. There is a kind of music in Saturn's system. Not sound. Space is not a medium for sound waves, but something analogous. A set of rhythms and harmonies played out in orbital mechanics and gravitational resonances. That structure the entire system like a composition. certain frequencies that recur, certain ratios that repeat, certain relationships between orbits that are not accidental, but are the inevitable outcome of billions of years of gravitational tuning. The concept is called orbital resonance, and it appears throughout the solar system, but nowhere more richly or with more observable consequences than around Saturn. We have already seen it in the rings, how Mimas and other moons carve gaps in structure through resonant orbital relationships. But the resonances among Saturn's larger moons are equally profound and even more consequential for the lives of those moons. Enceladus is in a 2-1 orbital resonance with Dione. For every orbit Dione completes, Enceladus completes exactly 2. This means that every other orbit, Enceladus and Dione pass closest to each other at the same point in their respective orbits, and the gravitational nudge Enceladus receives from Dione is always in the same direction. Over millions of years, these accumulated nudges maintain an eccentricity, a slight deviation from a perfectly circular orbit in Enceladus's path around Saturn. That eccentricity is critical. If Enceladus orbited Saturn in a perfect circle, the planet's gravitational pull on the moon would be constant, and there would be no tidal flexing, no squeezing and stretching of the moon's interior. But because Enceladus's orbit is slightly elliptical, the distance between Enceladus and Saturn changes as the moon goes around, closer on one side, farther on the other. Saturn's gravity is stronger when Enceladus is closer, weaker when it is farther. The differential tugging squeezes and releases the moon in a continuous cycle. It is this tidal flexing that generates the heat inside Enceladus. The energy comes not from radioactive decay or residual formation heat, but from the gravitational interaction with Saturn, ultimately from the orbital energy of Enceladus and Dione, slowly converted to heat inside the moon through the mechanical stress of tidal deformation. Life in Enceladus's ocean, if it exists, is powered by Saturn's gravity. The planet's tidal forces are what keep the ocean liquid, what drive the hydrothermal activity, what create the chemical gradient that organisms could use as an energy source. Without the 2.1 resonance with Dione, without the orbital eccentricity that resonance maintains, Enceladus would freeze solid. No ocean, no plumes, no candidates for habitability. Scientists soon discovered that the tidal relationship goes in both directions. Saturn is not a perfectly rigid body. When Enceladus orbits and exerts its own tiny gravitational pull on Saturn, the giant planet deforms slightly, a bulge raised by Enceladus's gravity, barely measurable, an almost infinitesimal response. But over millions of years, the gravitational interaction between Saturn's tidal bulge and Enceladus transfers angular momentum to the moon, slowly pushing Enceladus's orbit outward. The moon is spiraling away from Saturn very slowly, not dramatically, not at a rate you could observe in a human lifetime, but measurably over geological time. This is the same process that is causing the moon to move slowly away from Earth. Earth's tidal bulge, raised by the moon's gravity, transfers angular momentum to the moon's orbit, and the moon is currently receding at approximately 3.8 centimeters per year. Cassini measured Saturn's tidal interaction with its moons during close flybys and found something remarkable. Saturn's tidal effect is stronger than theoretical models predicted. The moons are migrating outward from Saturn faster than expected. This has implications for the age and history of the Saturnian system. It suggests that the moons we see today in their current orbits may have been significantly closer to Saturn in the relatively recent geological past. It also implies that the resonance between Enceladus and Dione, the resonance that powers Enceladus's ocean and makes it potentially habitable, may itself be relatively recent. If the moons were closer together in the past, they may not have been in the 2-pole-1 resonance. The resonance may have been established as the moons drifted outward and their orbital periods converged on the resonant ratio. Enceladus's ocean may be young. The habitability of Enceladus, the condition that makes it the most exciting candidate for life in the outer solar system, may not be a stable, ancient feature, but a relatively recent development, created by an orbital configuration that is still evolving. The window of habitability might be closing as the resonance slowly evolves and the tidal heating gradually changes. But that wasn't the strangest part. The resonances among Saturn's moons also predict the future. By modeling the current orbital configuration and running it forward in time, scientists can see what the system will look like in millions of years. Titan, currently the most distant large moon, will continue to migrate outward. Eventually, it will approach resonance with other distant moons. The small inner moons will continue to be sculpted by their interactions with the rings. The rings themselves will continue to lose material and thin. In hundreds of millions of years, the ring system will be gone. The small inner moons may lose their ring sculpting role. The tidal heating of Enceladus may change as its orbital configuration evolves. The ocean may freeze, but Titan will still be there. Large, warm relative to its surroundings, buffered by its thick atmosphere, potentially maintaining subsurface oceans fed by radiogenic heating from its rocky interior for billions of years more. What happened next, or rather, what will happen next, is being written in the slowly evolving dance of Saturn's moons, playing out across timescales that dwarf human civilization. The gravitational music of Saturn is not a static composition. It is a piece that has been playing for 4 billion years and will continue long after every memory of our civilization has faded. We are hearing a few notes of it, a few measures, a brief window into a symphony of unimaginable length, and in those few measures, what we hear is extraordinary. Every story reaches a moment where the known gives way to the unknown. We have traveled far through Saturn's secrets. We have stood inside the rings and watched their ice collide. We have looked down into the hexagon and felt its impossible geometry. We have floated above Titan's orange haze and imagined what moves beneath it. We have drifted through Enceladus's plumes and tasted the ocean water ejected into space. But for all that Cassini taught us, and it taught us more than any previous mission, more than the sum of everything that came before, the questions it raised outnumber the questions it answered. And this is where science is right now. In the second decade of the 21st century, cataloging the questions, designing the instruments, planning the missions that will go back. 3 major mission concepts are competing for the next phase of Saturn exploration. The first is an Enceladus life detection mission. Various proposals have been developed with names like Enceladus Orbilander or simpler plume flyby spacecraft that would return to Enceladus specifically to search for biosignatures in its plumes. These missions would carry mass spectrometers capable of detecting amino acids, lipid-like molecules, and other chemical indicators of life flying through the plumes repeatedly, sampling the ocean water that Enceladus is so generously ejecting into space. The scientific case for such a mission is extraordinarily strong. Enceladus provides access to a subsurface ocean without the need to drill through kilometers of ice. The ocean is bringing itself to us. And the potential payoff, a definitive answer to the question of whether life exists beyond Earth, is the most significant scientific result in human history. Scientists soon discovered that the Enceladus mission faces a significant technical challenge: cost and time. A dedicated Enceladus orbiter or lander capable of the science needed would be expensive. The journey to Saturn takes 7 years. The instrumentation required is sensitive and complex. Funding competitions are fierce. The mission has been in the proposal stage for years, competitive with other high-priority targets. The second major mission concept is Dragonfly, which we have already discussed. The rotorcraft lander for Titan, formally approved by NASA in 2019, currently in development for a launch in the 2030s and arrival at Titan in 2034. Dragonfly represents a different approach to the astrobiology question. Rather than sampling an ocean, it will walk through the chemistry of Titan's surface, looking for organic complexity that might represent a different kind of prebiotic or potentially biotic chemistry. The third concept involves return visits to Saturn itself, orbiter missions that would pick up where Cassini left off, with improved instruments for measuring the interior, the magnetic field, the ring system with higher resolution, and the atmospheric composition. Proposals for Saturn atmospheric probes, small entry vehicles that would descend into Saturn's atmosphere, measuring temperature, pressure, composition, and wind speed at different depths, are under development, motivated by the science return that similar probes at Jupiter have demonstrated. But the most speculative and perhaps most exciting future of Saturn exploration involves something that current technology cannot do, but that some researchers already think about seriously. A probe that descends deep into Saturn's atmosphere, past the cloud layers, past the supercritical hydrogen zone, into the region where metallic hydrogen exists. We have never directly sampled metallic hydrogen. We have never sent any instrument into the extreme pressure regime of a gas giant interior. The physics of what happens there, the behavior of hydrogen at millions of atmospheres of pressure, the details of helium rain, the structure of the fuzzy core, are inferred from external observations and theoretical models. A direct measurement would be transformative. Such a probe would not survive the descent, of course. No material we know of could withstand the pressures it would encounter. But it could transmit data for as long as it survived, minutes perhaps, sending back readings from pressures no probe has ever reached, before the increasing pressure crushed it into silence. Scientists sometimes describe this as the ultimate deep space probe, a messenger that descends into the planet, sends back what it sees, and is consumed by the environment it is studying. A sacrifice for knowledge. There is something poetic in that, and something fitting, the same relationship between probe and planet that Cassini's grand finale embodied. Meanwhile, back on Earth, new telescopes are coming online. The James Webb Space Telescope, the successor to Hubble, with a mirror 7 times the area and sensitivity across infrared wavelengths that Hubble could not access, has already begun observing Saturn and its moons. Webb's instruments can see thermal emission from the ring material, can detect molecular signatures in Titan's atmosphere with unprecedented sensitivity, can map the temperature structure of Saturn's atmosphere in ways that complement Cassini's data with new dimensions of information. Webb has already returned stunning images of Saturn, but more importantly, it is taking spectra, breaking the light from Saturn and its moons into its component wavelengths and reading the chemical fingerprints embedded in it. In Titan's atmosphere, Webb is detecting molecules that Cassini's mass spectrometers were too coarse to identify. New molecular species, new chemical reactions, new clues to the atmospheric chemistry of a world we thought we understood. And yet another mystery emerged from Webb's early Saturn observations. The rings appear different in Webb's infrared wavelengths than in visible light. Compositional differences between ring regions that were subtle in Cassini's data become pronounced in the infrared. Thermal patterns within the rings, temperature variations that indicate different physical states or compositions of the ice, are visible in a way that was not accessible before. The rings are revealing new complexity even to observers who thought they knew them well. What does Saturn look like to a civilization 1,000 years from now? To a humanity that has perhaps sent crewed missions to the outer solar system, that has established observatories on Titan's surface or in orbit around Saturn, that has sampled Enceladus's ocean directly and found, or not found, the life that we today can only theorize about? We cannot know. But we can know this: the questions will be different. The mysteries that consume our attention today will have been answered or replaced by deeper mysteries, or found to be unanswerable with any technology we can imagine. And the new questions will be stranger and richer than anything we can currently ask. That is the nature of Saturn. Every answer is a door. Every door opens onto a larger room. And the room is always larger than expected, always darker in the corners than the light can reach, always containing something that wasn't in the catalog of expected wonders. Saturn has been here for 4.5 billion years. We have been looking at it seriously for 400. We have not even begun to understand it. And that somehow is not a frustrating thought. It is a comforting one. Let us pull back, slowly, from everything we have seen. Let the hexagon shrink. Let the rings become a thin line. Let the moons, all 146 of them, become points of light orbiting a point of golden light. Let Saturn become what it looks like from Earth on a clear night, a steady, yellow-white object in the darkness, unremarkable until you know what it is, and then impossible to look at without feeling something profound. There is a photograph taken on September 15, 2006, by the Cassini spacecraft. It is called In Saturn's Shadow. Cassini had positioned itself behind Saturn in the planet's shadow, looking back toward the inner solar system. From that vantage point, the sun was hidden behind Saturn's disk. Its light filtered through the edges of the atmosphere into a thin, luminous arc of blue and gold. The rings were lit from behind, revealing structures and details invisible in front illuminated images, a kind of X-ray of the ring system, showing layer upon layer of material. And in the lower left quadrant of the image, visible only to those who knew to look, a pale blue dot, barely distinguishable from the background stars. Earth, we are in that image. All of us. Everyone who has ever lived. Every empire and war and love and discovery, every forest and ocean and mountain range, every person sleeping and waking, grieving and celebrating, all of it contained in a dot so small that it would disappear if the image were slightly degraded. Carl Sagan, when he asked Voyager to take a similar image of Earth from near the orbit of Pluto in 1990, wrote about the smallness and the humility that image provoked. He wrote about the pale blue dot, about the arrogance of thinking that we matter in some special way, about the responsibility we have toward each other and toward this fragile world, given that it is the only one we have. But there is another way to look at that pale blue dot in Saturn's shadow, a way that does not diminish us, but instead magnifies something extraordinary about what we are. We are the part of the universe that looked at Saturn and asked why. Not the brightest part, not the most powerful, not the most enduring, but the part that, in this brief flash of cosmic time, became aware of the existence of Saturn, aware of its rings and its moons and its storms, and cared deeply about understanding all of it. We built instruments. We launched them across the solar system. We waited years for them to arrive. We stayed up through the night to process the data. We wrote equations and ran simulations and argued with each other about competing interpretations of evidence gathered 886 million miles away. We made Cassini, and Cassini found Enceladus's ocean. Something in that chain of causation seems almost miraculous when you hold it in your mind all at once. The universe made hydrogen, and hydrogen made stars, and stars made heavier elements. And heavy elements made planets, and one of those planets made oceans, and oceans made life, and life made curiosity, and curiosity made spacecraft, and spacecraft revealed that other oceans exist, in other parts of the solar system, potentially teeming with something we have not yet met. The universe seems in some strange way to be investigating itself, using us as the instrument. Titan's lakes are older than our civilization by billions of years. Enceladus's ocean may be feeding living things that have never experienced sunlight, never seen a sky, never known anything except the warmth of hydrothermal water and the chemistry of dissolved rock. They have been there, perhaps, since before the continents of Earth took their current shape. They have existed in their ocean, going about whatever passes for their lives, while on a distant planet, mammals evolved and stood upright and built cities and looked up at the night sky and slowly, painstakingly, figured out how to send a machine to look for them. What does any of it mean? That question is not scientific. Science does not answer meaning questions. It answers mechanism questions, process questions, structure questions. The meaning question is for each of us to sit with quietly, in the way that quiet invites. But perhaps this much can be said: the fact that Saturn is beautiful seems significant. Not in a mystical sense, in a human sense. Beauty is what we experience when we perceive complexity and order together, when scale and pattern combine in a way that exceeds what we expected. The rings are beautiful because they are both enormous and geometrically precise. Titan is beautiful because it is alien and familiar at once. Enceladus is beautiful because it holds mystery in its silence. We are creatures built to respond to these things. Somehow, in the long history of life on Earth, we became beings who are moved by the sight of Saturn through a telescope. We did not need to be. A species can survive perfectly well without any interest in the outer solar system, and yet here we are, moved, that response, that sense of astonishment, that quickening of something in the chest when you see a new image of Saturn's rings feels like it means something, like it is part of what we are for, not all of what we are for, but part of it. Galileo saw Saturn in 1610 and wrote that it appeared to have companions on either side of it. He was confused. He didn't know what he was seeing. He would spend the rest of his life wondering. And now, 4 centuries later, we have been there. We have orbited it. We have touched its atmosphere and tasted its rings and found oceans on its moons. We know things about Saturn that Galileo could not have imagined even in his most expansive moments of wonder. And we are more confused than ever. There are questions Saturn is holding that we don't yet know how to ask. There are mysteries in its interior that we don't have the instruments to approach. There are answers in Enceladus's ocean that are waiting for a mission we haven't yet built. The mystery of Saturn is not a problem to be solved and filed away. It is a relationship to be maintained. A conversation that has been going on for 4 centuries, getting richer and more complex with every generation that joins it. Tonight, if the sky is clear where you are, you can step outside and find Saturn. It is visible with the naked eye. It looks like a star, steady and yellowish, not twinkling the way stars do. If you have binoculars, you can almost make out the rings, a slight elongation, a disc-like quality to the light that stars don't have. Through even a small telescope, the rings are unmistakable. That point of light has been there every night of your life, whether or not you were looking. It was there before you were born. It will be there long after all of us are gone. Ringed, storming, hiding its oceans and its secrets and its impossibly perfect geometry. Floating in the dark. Patient, waiting to be understood. We will keep looking.